Okay, we're going to do the presentation on section 6.5. So this equation, 0.3 e to the negative 0.3 t, as t gets bigger, it's a decreasing exponential. It goes off to infinity this way, this gets closer and closer to 0. And if we go from 0 to, say, b, we'll have a finite area. But if we go to infinity, we're going to keep adding more and more area. So is that always going to go infinitely large, or is it possible to keep adding an infinite number of terms or an infinite number of pieces of area and still have it not go unbounded, not blow up, have more than will approach a limit? And I'm going to give you an example of a series that does that. For example, a paradox, a legendary paradox, is one where, say, someone, I think it was William Tell or whoever it was, shot an arrow to knock the apple off of his son's head. And the paradox is this, that the arrow will have to go halfway, and that will take some time. And then it'll have to go halfway again, and that will take some more time. Less than the first, but still more time. And then it'll have to go halfway again. So this is the tip of the arrow. And each time it has to go halfway, and each time it goes that halfway, it takes a piece of time, and it'll be an infinite number of halfways. And so some people argue that, oh, well, it'll never get there because you're going to add up an infinite number of time chunks, which will get very, very large. But in reality, let's say it's estimated to take a second to go all the way to the apple. Then to go the first half, it's going to take a half a second, and then it's going to take a quarter of a second to go that next halfway, and then the next halfway is only going to take an eighth of a second, and the next halfway is going to take a 16th of a second, and the next halfway is going to take a 1/32nd of a second, plus so on. So here we have an infinite set of, and this will go on forever, infinite set of finite quantities. How much does that add up to? Well, let's just start adding. A half plus a quarter is 3/4. 3/4 plus an eighth is 7/8. 6/8 plus 1/8, 7/8. 7/8 plus a 16th, that's 14/16 plus 1/16, is 15/16. Add a 32nd, it becomes 31/32, 31/32. And you can keep going, and the numerator will always be 1 less than the denominator. And so if we kept adding here, we would never get the numerator to equal the denominator, which would be 1, but it's going to get infinitely close to that. So, it's going to be 1 billion and 1 billion minus 1 over 1 billion, which is really close to being 1. In fact, this converges, it approaches 1. Okay, so you can add up an infinite number of pieces and it will be bounded. It will have a limit to its size, as opposed to being unbounded, growing without bound. That would be called a divergent if it grows without bound. Okay, now how do you handle integrating that, finding this area under one of these curves? So this, you would change this to the limit as b goes to infinity and put b in place of the problem. You would integrate this So this would become the limit as b approaches infinity of the integral of this 0 to b of 0.3 e to the negative 0.3 t. That's, I'm just rewriting this, dt. And now to integrate that, I'm going to do a u sub for that power. So I'm going to let u equal negative 0.3 t. du would equal negative 0.3 dt. So this would become the limit as b approaches infinity of the antiderivative of the integral. I'm changing my limits because I'm going to u, and if t goes to 0, negative 0.03 times 0 is 0, so that would still be 0, and b would turn into u for the b would be negative 0.3b, and this would become 0.3 e to the u, and then we also get see, dt will become du over negative 0.3. So the 0.3's cancel, the negative doesn't, so I'm going to get still got to do the limit. I'm going to move over to here, still have to do the limit, so I got limit as b goes to infinity. The antiderivative, I'm going to have a negative, but the antiderivative of u, e to the u, is e to the u. So that's going to be negative because of the negative there. E to the u, but u was negative 0.3 t. And I need to evaluate that from 0 to b. So using the fundamental theorem of calculus, I'll plug the b into here, and then I'll plug 0 in, not taking the limit yet. I haven't tried to figure out what's going to happen to this as b goes to infinity. I'm going to get negative e to the negative 0.3b minus a minus, so plus e to the negative 0.3 times 0. Well, that times 0 is 0, e to the 0 is 1, so this is just 1. And this we have to look at what's going to happen when b goes to infinity. Well, does this explode or does it go towards 0? Well, you can see that e to the negative 0.3 is going to get closer and closer to 0. So this, when b goes very, very large, this goes to 0. Even though it's negative, which just flips it over, it's still headed towards 0. So this turns out to be 1. Yeah, 1. That's what this works out to be. So this area will add up to be equal to 1 unit. Okay, so let's do some more of these. So we'll take a look at, get some paper here. Hang on. Come on there. Let's take a look at what happens with this one. So we have the problem as it goes to infinity. So I'm going to say the limit as a or b or any letter you want to use for this. I'll use a this time. The integral from 1 to a of 1 over x squared dx. And to integrate this is x to the negative 2. The antiderivative of that is add 1, so it's x to the minus 1 divided by minus 1, which is just negative 1 over x. So this becomes the limit as a approaches infinity of this with a put in it, so it's minus 1 over a, minus a minus, so plus 1 over 1, and as a gets very large, the fraction 1 over a goes to 0, and so this becomes just 1. This process of seeing what happens as a goes to infinity is doing the limit. Up till then, I was just doing the algebra on the rest of it. So this would have an area under this curve. By the way, 1 over x squared looks like a little bit further away from there and gets close to this pretty quickly, close to the x-axis. But it's more spacey up here and closer there. Okay, let's do this one, which is almost the same, but we have the problem is a different place. Now, there's no way this can be a division by 0 because 1 plus x squared is always positive, so this doesn't we don't have a problem with this being 0, but we do have a problem with x going to infinity. How do we handle that? Now, the graph of this looks something like gets up to 1 and then it goes like that. So it's a chance that as we go to negative infinity from 0, that this area, even though it goes infinitely far, will have a limit. The limit, though, that's the concern here, or the integration limit, is that infinity. So we're going to go, let's find the limit of, as a goes towards negative infinity, of the antiderivative or the integral, and we're going to put an a there, and 0 here, of 1 over 1 plus x squared dx, and 1 over 1 plus x squared is it's the derivative of arctangent, so the antiderivative is arctangent of x. And then we're going to put these two in for the limit, so we're going to put an arctangent of 0 minus arctangent of a. And now we want to know what happens as a approaches negative infinity. Okay, so let's, to have a better idea of what's going on here, let's graph arctangent. So I'm going to go y equal, I'm going to clear that and go in arctangent, which is tangent inverse, second tangent inverse of x. Graph. And that appears as a goes to negative infinity, this appears to approach a value down here. Let's just kind of trace and see what that's getting closer and closer and closer to. It looks like it's getting closer and closer and closer to negative, I'll hold it up here so you can see it better. Maybe you can see better. Negative 1.4. What this approaches is negative pi over 2. Because this is, if you look at it this way, this is a tangent. It's a tangent curve turned upside down, but tangents have asymptotes at pi over 2. Let me show you that. I'm going to go to y equal and type in negative pi divided by 2. Graph. Do you see how it's getting closer and closer to negative pi over 2? And tangent of 0, arctangent of 0 is 0. So this is 0, and this approaches negative pi over 2 as a gets very small, goes to negative infinity, and so this area under the curve is negative pi over 2. Okay, now they say, what about this one? And they're going to infinity on both sides. Okay, so what's this curve look like? So we're going to go to e to the negative of x squared. Well, it looks like it goes to 0, and it looks like it's very symmetric. Because of the symmetry, we can do this with one interval. We can say it's going to be whatever it is from 0 to infinity of e to the negative x squared dx, and just double it. Now, the alternative for doing that is to, when we change this to limits, excuse me, let's go back up here. When we change this to limit, we're going to have 2 times the limit as a approaches infinity of the integral from 0 to a of e to the negative x squared dx. Okay? That's what we'd have to work out. Now, if we kept it with the both of the infinities, we'd have to do, well, let's see what happens as a goes into infinity, as well as what happens as b going to negative infinity of the integral of b to a e to the negative x squared dx. That's how you would have to set that up if you were trying to do it with the a's and b's. Anyway, what is the antiderivative of e to the negative x squared? That one's a little tricky to do. Let's see if we got anything in our formula page for that. And I am not seeing something right away. We would probably, let's see, let me think about this. I think we would, this is going to fade, and we'd have to figure out what that is. I'm not sure I like that. Okay, I'm going to do a u sub. Negative x squared, then du would be negative 2x dx. And yeah, I don't like how that's working. I'm not sure how to integrate that right now, but that's how you would set it up. So I'm just going to leave that there. This is what we'd have to figure out. Now we can go to Wolfram and type that in and integrate that. U sub's not going to work very well. By parts might work. I'm not sure. So I'm going to leave that. Okay? All right. Now, this activity, number 6.5, they're going to have you look at y equal 1 over x. And that becomes pretty important in this whole business, because a lot of these ones that we think might be able to add up the area are ones where the area gets smaller and smaller and smaller that way, or gets smaller and smaller and smaller if you get closer to this axis. And 1 over x is important. So let's go ahead and do that one. So we'd have to do the limit as a A or B, I'll do A approaches infinity of the integral from 1 to A of 1 over x dx. Now we want to completely work this one out, even putting in the limits, and so we have the limit as A approaches infinity. Well, 1 over x is ln x, and then we're going to put in the A, so it's ln A minus ln 1. That's putting in the 1, the A first, and then the 1 second. And now we have to figure out what happens to this as A gets very large. ln of 1 is 0. But ln of A, as A goes off to infinity, we have to remember what ln graph looks like, and it looks something like this. And so if we're going A going to infinity, this just keeps going up and up, and so this goes to infinity. So this is unbounded. And it'll turn out, if you go from 0 to 1, which they didn't do here, that area is also unbounded. But if we get a curve that stays below that all the time over here, that will be bounded. Or if we have another curve that goes closer, stays closer than this to this, it will be bounded. Y equal 1 over x is the borderline between what will be bounded and what will not be bounded. Which brings us to this one, where we're doing the integral of 1 over x to the 3/2. So let's compare 1 over x and 1 over x to the 3/2. Clear? 1 divided by x and 1 divided by x to the 3/2. Okay, so let's push zoom 4. That's 1 over x. Do you see how it's further away here? So if we were going from 0 to some value here, the red would be unbounded also. It's bigger than 1 over x. But to here, it's closer to the axis, and so it will be bounded if we go off to infinity. And what did they want us to do here? Go to infinity. So I'm going to take the limit as b goes to infinity, could have been a, from 1 to b of this dx, to integrate x to the, see, this is x to the negative 3/2. So I have to add 1 and divide by what I get. So adding 1 to negative 3/2 is negative 1/2. So the antiderivative would be x to the negative 1/2 divided by negative 1/2. That turns into negative 2, and this is the square root of x in the denominator. So this becomes the limit as b approaches infinity. I'll put b into this, so I get negative 2 over the square root of b minus a minus, so plus 2 over the square root of 1. Well, as b goes to infinity, this denominator will go to infinity, so this whole part will go to 0, and this part will be what I get for my answer. 2 over the square root of 1 is just 2. So the area from 1 to infinity, under the red curve adds up to be 2. Okay, so now they wanted us to go through and investigate that one, and I did, and then they want us to investigate this one, and I did, and they said plot them. We did, and we find out that this one is closer to the x-axis than this one as we go to positive infinity. It is bounded, that one is not. That's the whole point of activity 5.6. So, this is closer on the infinity side than 1 over x, so this one will converge. This one, even though it's got plus 5, which shoves it sideways, as you go to infinity, this is 2/3, and 2/3 is smaller power than 1, so this one will diverge. And we can go through and work these out, but that's what's going to happen. This one, which is bigger than 1, makes this denominator larger, so this one will converge. And this, if we're going to infinity, as long as p is greater than 1, this will converge. And you could actually do it with a p in there, and you can figure out that it approaches 1 over p minus 1, I think it is. It's in problem 7 they do that one. Now what about these? Well, this one that one's easy enough to integrate, and this one is easy enough to integrate. Let's go through and actually do those. So, we'd say the limit as b approaches infinity of the integral 0 to b, or it could be a and a, and we're going to have to do this one by parts. So this is going to be x for u, and v, we're going to put the e to the negative x over 4 dx. To integrate this, it would be e to the negative x over 4. And if we take the derivative, we get minus 1/4, but we don't have the minus 1/4, so this has to be minus 4, the antiderivative. You can do a u sub on that, then integrate this, and you'll get this. Derivative of x is 1 dx. So the integral from 0 to b of x e to the minus x over 4 dx becomes, we haven't taken the limit yet, so b still got to go to infinity, of uv, which is x e to the negative x over 4, and then would have left and that would have to be evaluated from 0 to b minus the integral from 0 to b of these two, which is minus 4 times 1 e to the minus x over 4 dx. And so then we'd have to go another time here and find the limit as b approaches infinity. If I put b in here, I'm going to get b e to the minus x over 4 minus 0 times this, which is going to be 0. 0 times this, and this would be e to the 0, which is 1, but it's times 0, so it's 0. That's this part. Now we still have to integrate this. I'll do a u, well, if you do a u sub, you're going to get the negative 4 e to the negative x over 4. Yes. And we already had a 4 out there, so it's going to be minus 16 of this. We got this part, which we've figured out, minus, oh, and there's still the limit as b goes to infinity, minus 16e to the minus x over 4, evaluated from 0 to b. Wait a minute, it's plus 4. No, we get a minus here. 4 times a minus 4 is negative 16. So we put the b in, and we get 16e to the minus x minus b over 4 plus 0. Put 0 in there, and we get minus 16. So we get minus, we put the b in, we get minus this, and then we go minus a minus, so it's going to be plus, and put 0 in there. That's 1 times 16, which is 16. So we have all of this. We have to decide what happens as b goes to infinity. Well, e to the negative is going to go closer and closer to 0. This b gets infinitely large, but this gets infinitely small. And to figure out what happens here on this part, we need to use Hopital's rule. We're trying to find the limit as b approaches infinity. And so I'm going to put b in the numerator, and I'm going to move this to the denominator. And this is e to the x over 4. Becomes a positive if we move it down. This goes to infinity. This goes to infinity. And so we can take the derivative of both of those, and we get the limit as b approaches infinity of the derivative of b is 1. Actually, this is x. I shouldn't have put b in there. X. And no, we're putting b in there. So those are both b's. Should have put a b in there. This should have been a b. The derivative of b is 1. The derivative of e to the b over 4 is 1/4 e to the b over 4. This still goes to infinity. This goes to 0. So this whole thing goes to 0. So this is 0 as b goes to infinity. That's 0. This goes to 0, and that's 16. So that's 0, 0, 0, 16. So this has a total area of 16 under this as it goes to infinity. This was just this part of this, which would go to 16 also. And so these converge. Okay. Almost done with this. That was more than what I did in the class. Now, what's the issue with this one? Well, if x was 2, this would be division by 0, which is right in the middle. And they've drawn a picture of this. This is this curve separated. Now, remember that 1 over x is the borderline. This is lower than the 1 over x. If I moved it over to minus 2, the 1 over x would be above here and would be in here. So this area is bigger than the 1 over x, so it would diverge. And so would this. Now, they went through and did this, but to do this, we'd have to do it in 2 pieces, or you could just do one. They said, well, we have to go from they went from 1 to negative of 2 from the negative side, and then from 2 from the plus side to 3. They split it into 2 pieces. They did this one and this one. I would have said these two are going to be the same, and so I would have done just twice this one. And this will, as if we're going to this line, is going to diverge, just because of what we know about the 1 over x thing, this shape of this, okay? And this one, the problem's at 0, so you would have to do that. But x to the 1 over x to the 1/3. Let's go to there, and that's 1 over x to the 1/3. That's really just, I'll do that. 1 divided by 3. Let's just see what that looks like. That's the 1 over x. If we're going to go between 0 and 1, that one will converge, and they want you to figure it out. So you would do a limit as b goes to 0 and put a b here, integrate that, and work it out. I believe that one will have a limit. Oh, we're going to 0 to 2, and there is e to the negative x looks like this, so there's no problem between 0 and 2. This is just going to be a normal integration. We don't have to do any limits. This one will converge. This is going to be a finite value. This one, you have to check. The problem is at 0. This one, 4 is a problem because it becomes 4 minus 4. And what will that look like? So let's take a look at that. 1 over parenthesis. Let's get rid of some of the stuff here. Well, I can put a 2 there, come back here, and put in 4 minus x parenthesis to the 1/2. Okay, so that's what this one is. Let's graph it. There's that curve. And we want to do it from 1 to 4, and 4 is where it goes up. To see whether how that matches with this curve, I'm going to take this one, turn it over, and move it over. So I'm going to turn it over by inserting a minus, and then I'm going to move it over 4. So I'm going to go parenthesis x minus 4. So there's this one, and there's that one, and it looks like it's closer to the 4, so this one will converge. But you can go through the math and do that one. It's just this to the minus 1, and you do a u sub for what's inside. You would do a limit on this one as b goes towards 4, and put a b there and work it out. This one from minus 2 to 2, that has a problem at 0. So let's take this one, delete, go up here, delete that and make it over x only. And this is 1 over x squared. X, cut it out, get up there, delete, there we go, graph. So there's that one, and if we're doing it going close to 0, because the zeros are a problem, and so this is the one where we'd have to split it into 2 halves, but it's so symmetric that we don't need to do from 1/2 and double the answer. But this gets further and further away, so this one's going to explode. So this one will diverge because it's further away from the axis than the blue, the 1 over x. How about the tangent? Tangent, you can't use the graph like that, so let's integrate this. Where's the problem? What's the tangent of 0? Well, that's 0. What's the tangent of pi over 2? Tangent of pi over 2 is undefined, so that's the problem. So we have to go limit as b approaches pi over 2 of tangent of x integrated from 0 to b dx. And the antiderivative of tangent is, pulling up my sheet here, is the natural log of secant. So this would become the limit as b approaches pi over 2 of the natural log of the secant of b minus the natural log of the secant of 0, and then we're going to find the limit as b goes to pi over 2. Well, secant is 1 over cosine. And cosine at pi over 2 is 0. So what's inside of this is going to go to infinity, and the log of something going to infinity will also all go to infinity. So this one is going to diverge. And between 0 and 1, 0 is not a problem, but 1 causes division by 0. So this is what we'd make b, and we would use, let's see, that's arc sine. That's the antiderivative of this is arc sine, so we'd have the limit as b approaches 1. That's the problem, because it becomes 1 minus 1, of arc sine of this. We would be changing this to b, so we put it b minus arc sine of 0. And if for what angle is the sine 0, this would be pi, would be 0. And for what angle is it 1? Sine is 1 at pi over 2. And so this comes out to be just plain old, as b goes to 1, we can do arc sine of 1, it's pi over 2. This is just pi over 2. So this one converges. Okay.